Both least squares and maximum likelihood produce one suit. But what if the tailor isn't sure about the measurements? What if she wants to express her uncertainty? This waist measurement is reliable, but the inseam is less certain. The Bayesian approach doesn't make one suit. It makes a probability distribution of suits. Full Bayesian estimation generates a posterior distribution over all possible suit parameters. Not one waist measurement, a distribution, probably 32 inches, but could be 31 or 33. Not one shoulder width, a distribution, most likely 80 inches, small chance of 17 or 19. Each possible suit in the distribution as a probability weight how likely it is to be the true best fit. The tailor's answer isn't a suit. It's a wardrobe, each suit tagged with its probability. The Bayesian tailor brings experience. She's fitted 1,000 clients. Before she even measures you, she has a prior belief. Most men's waists are between 30 and 38 inches. This prior combines with your measurements, the data, to produce the posterior. If she takes many precise measurements, the data dominates and the posterior is tight. Waist is 32.3 plus or minus 0.2. If she takes few rough measurements, the prior dominates and the posterior is wide. Waist is somewhere between 30 and 34. Prior regularizes. It prevents extreme estimates from noisy data. The posterior gives credible intervals. The waist is 32 inches with a 95% credible interval of 31 to 33. This means, given the data and the prior, there is a 95% probability that the true waist is between 31 and 33 inches. This is not a confidence interval, it's a probability statement about the parameter itself. The Bayesian suit has error bars. You know exactly how confident the tailor is about each measurement and which measurements are uncertain. Tailor can't try every possible suit. There are infinitely many parameter combinations. Instead, she uses Markov chain Monte Carlo. Start with a random suit. Propose a small change, adjust the weight by half an inch. Check, does this change make the suit more likely to fit? If yes, accept the change. If not, accept it anyway with some probability to avoid getting stuck. After thousands of proposals, the chain of tried suits represents the posterior distribution. The histogram of sampled waist measurements is the posterior for waist. MACMA is the fitting process for Bayesian inference. In pharmacometrics, all three methods are used daily. Nonlinear least squares NNLM inner fits population PC models by minimizing squared residuals. FAST, the historical default. Maximum likelihood SOM and FOSI in monolix and non-MOM models the error structure explicitly and handles non-Gaussian data better. Bayesian Stan-Burns or metrics generates full posterior distributions for each patient's clearance, volume of distribution, and elimination rate constant. The Bayesian approach provides the credible interval for each patient's parameters essential for therapeutic drug monitoring, where you need to know how uncertain the dose recommendation is. One suit minimize gaps, least squares. One suit respects body shape, maximum likelihood. A wardrobe of suits with probability tags, full Bayesian. Least squares for standard bodies with Gaussian errors, fast and sufficient. Maximum likelihood for unusual bodies with non-Gaussian errors, more accurate. Same computational cost. Bayesian for situations where uncertainty matters, more expensive, but you know exactly how confident you are about every measurement. Choose the tailor that matches the client.